So we are happy to have Gabrielle Keller here to talk to us about parallel array programming in functional programming.
Welcome back, everyone. I hope everyone is sufficiently caffeinated to survive a post-lunch session. I'm going to talk about parallel functional array programming, and this is not working. Does anyone have another click thing? Just do it manually. So mainly basically about the implementation, or kind of some aspects of the implementation of parallel functional array programming. Just kind of to get a feeling, so who here is doing some work on parallel programming? So quite a lot, kind of more data parallel or control parallel? Data parallel, in which kind of context? Stencil programming. But I mean, generally, so I'm also going to talk about some aspects of the language I'm talking about is embedded domain-specific language. So about aspects of implementing performance-sensitive kind of domain-specific languages. So the issue with parallel functional programming is, like with parallel programming, there's basically one big reason why people would go to the effort of actually writing something in parallel, because it's a lot of work, it's a lot more expensive, and that's because they care about performance. And especially kind of on some of the hardware which is fairly cheap, like GPUs, hardware is cheap, but they're actually really, really painful to program. And you can see that, like, there's a whole paper by Mark Harris on how to implement scan efficiently for the GPU. And it's a really good paper. There's a lot of it. So it's a non-trivial task. And functional languages have a lot to go for them. They offer a high level of abstraction with all these nice things like higher order functions, controlled side effects, and so on. But usually performance is not the strength of functional programming. Like, no one kind of says, well, I wrote my program in Haskell or in ML because I really needed the speed. The compilers are by now pretty good, and performance for most applications is not a problem. But if you really care about the performance, functional programming often it's a lot harder to deliver because of the high abstraction level, where there's a lot more work to do. So the question is basically, can we kind of solve this problem? And how can we work together? Can we get it to work for us? And the good news is, I mean, they're not just downsides to abstraction, but abstraction, especially in the parallel context, actually also helps a lot because the compiler has a lot more information than in an imperative language. So it can, at least in theory, do a lot more aggressive optimizations. Then something functional programmers are already used to kind of collection-oriented programming style versus loop. And even though you can basically do everything with recursion in a functional programming language, that's kind of not that encouraged. It's a lot nicer if you can use higher order functions. So they are already used to that. And higher order functions like map, fold, they expose the parallel access pattern. And another thing, obviously not all functional languages are strongly typed, but some functional languages have really expressive type systems, and they help us in two aspects. First of all, like the obvious thing that good type systems help to guide the user and do a lot of static checking for you. And that's especially for more complicated problems like parallel computing, important. But also, and that's kind of a bit of the theme of my lectures as well, they're also really good for the compiler writer. If you're implementing something, if we're implementing the transformation in a strongly typed language, and it is hard to write a compiler for a for a parallel language, it's actually really, really helpful to try and maintain the types during compilation. So the language basically we're using is Haskell, and Haskell has all these kind of nice properties, and because Bob is not here yet, I can get away with saying it's pure functional programming. But we can kind of leave this discussion for Saturday or Sunday. But generally, like, it has a lot of nice properties. So can we kind of make them work for us? And I mean, one approach would be we integrate parallel programming into Haskell. And a lot of these issues are actually a real problem. And I'm really speaking from experience here because we tried that with data parallel Haskell. And that was a project where we wanted to have basically Nestle-style parallelism. I don't know, did Guy talk a bit about the Nestle programming model? So we wanted to have that in Haskell. And the whole project was, in some sense, a really successful failure. We never got there. Like, we made it, we had more and more basically example programs which ran really fast, but it was always really easy to write programs where the performance was really horrible. And because we actually changed the GHC, the Haskell compiler, and we relied on a lot of very fragile optimizations, it kind of worked for a while, and then someone who had worked on GHC changed something, and the performance went downhill. The good thing about the whole project was that a lot of the infrastructure we implemented for it, so the vector library for Haskell, repr, the whole type family idea basically was motivated by something we wanted to get done in data parallel Haskell. So we never really came close to achieving the goal we started out with, but we produced a lot of really things which people apparently found useful. And to a certain extent, Accelerate is basically a kind of spin-off project from that. So the idea is, if we can't get the full language to work, if that's just too hard, how about having just a domain-specific language, so not trying to kind of implement the whole thing, support everything, cut out a nice kind of manageable part of the whole domain and attempt that. So domain-specific languages is something like every one of us kind of works with all the time. They usually kind of have some specialized features for a particular application domain, and they don't need to be Turing complete, like languages like HTML, MATLAB, for matrix programming, SQL, PostScript, or LaTeX is a domain-specific language typesetting. So we're kind of all familiar with that. And an embedded domain-specific language is basically implemented as a library in an existing language. So it can integrate with the host language. And there are a couple of very big advantages to the embedded domain-specific language approach. One is we can reuse the syntax of the host language, which means we don't have to write a parser, type checker, all these things, which basically clear how you do it, but they are a lot of work, and they drain a lot of resources. And also the people tend to use embedded domain-specific languages more readily because even if you have a problem, you don't necessarily want to learn a completely new language. But if you can just download a package for your favorite language, then that's fine. And then we can use the host language to generate embedded code. So Accelerate is an embedded domain-specific language for high-performance computing in Haskell. And the way it works is you write your kind of Accelerate program in Haskell, you compile and run the Haskell program, and then at runtime, the Haskell program reifies, kind of generates the target code and runs it on, and that depends basically, we have multi-core CPU backends and GPU backends. So you run it, and then the result is fed back into the Haskell program, and this loop, depending on the application, kind of this loop repeats quite often. So if you have whenever look, so there are kind of a number of does it start? A number of examples in the Accelerate package. So there's a ray tracer. Ray tracing is quite nice to, kind of easy to implement in that model. And you can see that the CPU, so I don't have, it only works if you have a CUDA capable GPUs and NVIDIA GPU, which I don't have. So it runs here on the CPUs and a couple of other. So because it's really busy, it won't really react. Yeah, no, I can cut it. Yeah, so as long as you basically stay in these areas of array computation, ray tracing, fluid flow, Mandelbrot, and body simulations, so Accelerate is fine. It doesn't support any real kind of nested or irregular computations. So if you do have like sparse matrices, you have to manually kind of convert that to something like compressed row format or so on. So that's basically all we offer and what we focus on. Yeah. So a PhD student currently is working on a limited form of nested data parallelism for Accelerate, but so hopefully we can kind of offer that soon. So if you look at domain-specific embedded languages, there are basically two ways to embed the language in the host language. One's a shallow embedding, and the other is a deep embedding. So people know what the difference between shallow and deep embedding is? Shallow embedding is just kind of a fancy name for library. Kind of, you have a library, a domain-specific library. So the idea is the shallow embedding basically provides the fixed interpretation, and the semantics is kind of captured in the type. And let me give you an example. So let's assume we wanted to write our domain-specific arithmetic expression language, which doesn't make any sense because Haskell, of course, has support for arithmetic expressions, but just as a simple example. So with Haskell, I understand there was a kind of survey, and it looks like kind of 1/3 of the people have really no experience with Haskell. another third have some, and another third are fairly proficient. So I try to explain, it should be basically enough to follow the talk, the lectures, if you have a passive understanding of it. I will use some advanced features, so please don't hesitate. If there's anything, even if it's a basic thing, if there's anything you don't understand, please just ask. I'm happy to explain. So let's say we want to have this arithmetic expression, EDSL in Haskell. So what I do here, I just define a type synonym for arithmetic expressions. That just is like a C type synonym. So it doesn't give the type checker any extra information, or it just gives float a new name, which I can now use interchangeably. And then I add an implementation for addition, and so addition takes two expression values and returns an expression, and because it's already in our language, the implementation is just that it calls the regular addition. But let's say the language would be some kind of graphics description language, then it would be a lot bigger, but it would be a fixed interpretation. So I add all these operations I want, and then I can define a sample expression, and the sample expression basically is just a function call. And I use the evaluation mechanism of the host language. So as I said, it's really just kind of a library, nothing special here. Deep embeddings are a lot more interesting. It captures the domain-specific language expression as an abstract syntax tree. So what I do here, I define a completely new data type in Haskell to model these expressions. So what this means, I say, well, I have a new data type expression, and the expression data type has 4 different constructors. One is addition. Addition takes 2 expressions as arguments and returns an expression. And let me use, so this is a kind of alternative syntax, which I can only use if I switch on a language extension, but I think actually the syntax is nicer and clearer. So the alternative syntax is here, and here you can see more explicitly what the type of each of the constructors is. So a constructor really is just a function in some sense, but in contrast to functions in general, you can always reverse the application of a constructor. So if I apply add to 2 expressions, the add just puts the 2 expressions kind of in a box and gives me the box with a label on it, and then I can open the box and take out the 2 expressions. Whereas real addition, if I know that basically the result of an addition is 10, I can't know what the input values were. And with constructors, I can always unpack that, and the way to unpack them is pattern matching. And I think you did some kind of ML programming last week, right? And there you would have used pattern matching. So do that, and then I can define again a sample expression of a multiplication at 2 constant values, and all this really does, there's no evaluation happening. So all that's happening here is basically that internally, like, it creates this data structure, it creates this tree. And in practice, kind of in most deeply embedded languages, people don't expose the constructors. So just a quick side note, in Haskell, type names, not variables, but type names, and constructor names always start with uppercase letter, and functions and regular variables with lowercase. So often kind of they are wrapped in something which is called a smart constructor, a function that calls the constructor. In this case, the smart constructor is pretty dumb because it doesn't do anything, it just really calls the function, the constructor, but in general, the smart constructor could kind of check something or do more work, or kind of just provide maybe a more convenient interface. Okay. And now we can use that and provide kind of different interpretations for this abstract syntax tree. So, because for Haskell, there's now basically doesn't have a meaning associated with this tree. So I write here an evaluator. This is kind of the pattern matching where I take the tree and kind of disassemble it. If it's a constant value, and the type is, it takes such a tree and returns a floating point number. And if it's a constant value, then the result is basically just x, so it just takes it out. If it's an addition node, then I just have to recursively evaluate both subtrees and add the result, and so on. But I can also do other things with this tree before I evaluate it. For example, I can kind of implement an optimization. Now, again, there's not really much I can do, but I can simplify, and here just if I have two negations, then I just get rid of it. So I traverse the tree and return a new tree. I can do other things as well. So I can, for example, take the tree and generate C code from it, or generate anything else. So there are lots of things I can do with it. So in general, you want to have a shallow embedding if it's pretty much straightforward how to implement everything. And there are not a lot of optimizations and manipulations of the program you have to do. But if you need to analyze it, if you need to optimize it, then a deep embedding is the way to go. So another thing would be, for example, I could take an expression, generate code, and execute it on another device, and in which case it would be an I/O effect, which then, because it is on the device, and which returns a float. The problem with this representation is, though, that we have a strongly typed host language, but if you look at the data structure, if you look at the expression type, it's untyped. That doesn't really matter for this expression type as it is at the moment, because, well, the only type it can have is float. But let's just make it slightly more complicated and add a conditional and then a Boolean operation like less. And then we need two different constants, because less can return true or false. So we need a Boolean constant, and we need a numerical constant. So now we have the problem that we kind of have multiple types, or the expressions can represent either floating point expressions or Boolean expressions. But this information is completely lost in the representation. And then I have to do what a kind of dynamically typed language has to do, right? So my evaluator, what's the type of my evaluator now? So my old evaluator took an expression and returned a float. Sorry? Yeah, but then it's not really evaluated, it's simplified. So what? Do
you need parameters?
I need a new, because it can be float or bool. And so I need to define a new type, which can either contain float or bool. So I define here a type result, and basically all it does is kind of, it's a sum type where it's either float or bool. So I basically lose information both in the expression tree, but also the evaluator itself has less type information. And now, as a result, it gets a bit more complicated. So I take the Boolean value out of the box just to put it into another box. Same for constant. And now for conditionals, so I evaluate the condition, and then I have to, we have two types of pattern matching. One is in the function definition. Like here, when I match a pattern of the argument, or if I want to match on the pattern of an intermediate value, I use the case expression. So I call eval condition, and then I have to treat both cases separately. So if it's a Boolean constant, then depending on whether it's true or false, I pick the right or the left branch and continue evaluating, and otherwise I have a runtime error. I have a runtime error because I have this dynamic, so I shifted stuff from static checking into the dynamic world, which means, first of all, like, it's more work because I have to do this, like at runtime basically, I have to check all the labels, pack and unpack. Secondly, I have the potential for runtime errors, which are obviously not great. And then some things are actually hard to check. So let's say I want to, for conditionals, I want that both expressions have to have the same, then in the else case should have the same type. Then I can't check it in the evaluator. It's basically, it's just not a very kind of good situation. I have this expressive language, a strongly typed language, and I'm doing this, throwing all that potential away. So basically what we want to have is that the expression knows that the expression type tells me whether it's an expression of float or an expression of bool. So we would like to parameterize the expression with it. And well, we know about kind of parameterized polymorphic data structures. Let's say, for example, I can define a tree of any type, which can contain in the node any type of value. So I write tree has two constructors, a leaf, which can construct, because it doesn't actually carry an item in it, it can construct a tree of any type, and the node, which gets a value of type A, trees which contain values of the same type, and it builds a new tree of that type. And here I said these two notations are equivalent, but there's one thing which is different and which kind of looks similar. So in the first notation, basically the result type of the application of the constructor is implicit. So leaf does not have anything there, so it means it doesn't get an argument, and the result type is the type of the data structure I'm defining. So the result type is tree of A. And with node, I only mention the three arguments, but I don't mention the result type here. And in that notation, basically, the scope of this type variable A is this part. So it says basically for all A's, and then the scope of the A is in the whole body of that. This is different here. Here, tree A just says tree has one type variable, one type parameter. And then that's the end of the scope of the variable A. And then it's for all quantified here. So it says leaf has the type for all A node of A. And node has the type for all A. If I have an A, a tree of A, a tree of A, then I can produce a tree of A. So I can rewrite this and just not use A's everywhere, and I get the same result. Whereas up there, if I would kind of put A, B, or C in there, it would set, well, type variable out of scope. So this notation, this is called a generalized algebraic data type. And because the scope is different thing with it. So I said, well, we want to have a type parameter for expression, right? So the way we do that is we say, well, expression A. So this means expression has one parameter. Now I don't have to use the same A here. So what would be the type of ad? Sorry? Yeah, expression float, so it wants two expressions of type float, and it can return an expression of type float. So now with these generalized algebraic data types, I can basically, because the result type doesn't have to be the same as the type I define, I can specialize it and let it carries more information in it. Multiplication is the same. Negation, less then says, give me two floating point expressions and I'll give you a bool. Constant now, we don't need different constant expressions anymore. We just say, well, if you give me an A, then constant will wrap that A into the expression box and create an expression of type A. So we might not like that because I could actually put a function in there. I can now apply const of plus, and then I have an expression of function type. But that doesn't really matter. I can't do anything with it. None of the others, well, if actually kind of does work with it. But I could restrict that if I wanted to. And if wants an expression of type bool, an expression which will evaluate to bool, and it doesn't care what the type of the two branches is as long as it's the same. And it states that the result is the same. So now my evaluator gets a lot simpler again. I don't have to check anymore. So const just, and the type of the evaluator is now also, I don't have to define a result type where I throw everything in there. I just say, well, if you give me an expression of A and the evaluator is actually correctly implemented, then it should better give me an A back. And if not, then there's a bug in the implementation of the expression evaluator. So the Haskell compiler now proves part of the correctness of my evaluator for me. And it's also a lot less work. And it's faster because, well, I don't have to do this label checking at runtime, right? So now I can just no case expression here because I get basically the naked condition, the naked Boolean value, and I can use that straight away. I know it's a Boolean value. And then I call the eval expressions. So let's say if I write const true add of const true const 5, yeah, okay. So now basically I can't write an expression which is type incorrect because otherwise the type checker here complains until I fix this. And then it's happy. Similarly, if I write an eval function and write expression a, and const a is a, or anything else which wouldn't be kind of, then the type checker here already finds basically that something is wrong here. Or if I would return a floating point value, then I already basically get some kind of correctness proof for free. And the nice thing, I mean, this is really, we win on all fronts here, right? It's faster because I don't have to do any dynamic checking. It's less code to write and it's safer. Usually, I mean, that doesn't happen very often. Usually kind of, you know, you pay for things. With this, it's really kind of a win-win situation. And now, for example, with the simplify, again, we, like an optimization, should better preserve the type of the expression. And this, again, this property is the type checker proves this part of the correctness of my simplify function. And okay, in this expression, it's so trivial, like it doesn't seem like a big win. But in a really big, in a kind of complex program, it's so easy to get optimizations wrong. And most of the time, the type breaks. So having this, basically being able to express the fact that for my embedded domain-specific language, if I apply an optimization, it actually preserves the type, is really, really valuable. So let's finally actually kind of have a look at accelerate. So parallelism is basically introduced in the form of collective operations on arrays, and there's really nothing spectacular. It's kind of the usual function. So I get arrays in, accelerate computation, and arrays out. So we have maps, zipWith, folds, generators, lots of different permute operations, and stencil operations. So, one simple example of an accelerate program, but this is actually not an accelerate program, this is just a regular list, list.product. So, dot product takes basically, multiplies pairwise the elements of a list and then computes the sum. I have import prelude here, not because it's necessary. Prelude in Haskell is automatically imported and kind of provides all the basic, the standard functions, but I just have this here to emphasize the fact that these are just the regular predefined functions. So zipWith has the type, it gets a function which takes arguments A, B, C, can be any A, any B, or C. As long as the first list it gets has all elements of type A, second elements of type B, then it applies this function basically in lockstep fashion to every pair or the pairs in the zipped list, and it returns a list of the results. Fold left is the reduction, kind of a generalized sum. So it takes a starting value, and if the list is empty, it will just return this value B. If the list is not empty, it applies this function to the B it has. The first element of the list gets a new B, and so the B is kind of the accumulator. This thing, what does it mean to have this kind of num A implies dot P has the type a list of A to A. So addition obviously, like, we apply addition, we calculate the sum. So if I have a list of characters or a list of functions, that's not possible. So A can't be of any type, so there are restrictions on type A. And this basically says, well, A has to be a member of what's called in Haskell a type class num, and the type class really is just a set of types which have some certain properties, and the properties num has is the class num has the following operations defined on it. So if something is in num, then addition has to be defined, subtraction, multiplication, negate, and so on. And in Haskell, lots of, like, all the numeric types are already in type num. And if you define a new data type, then you can say, well, this new data type is an instance of class num. And here is how you add two numbers. Here is how you subtract two numbers. One thing that's really kind of discouraged, and there are lots of languages where you can basically add anything and the language comes up with some semantics, like you can add 5 to a string and so on. So in Haskell, the idea is that you should not be able, like, it's not enough to come up with some kind of strange interpretation of the function. They should actually observe the usual rules, so it should behave like plus, minus, and so on, and should be numbers. So even if you can come up with an interpretation for strings, which can you can make string a member of type class num, you really shouldn't do it. The compiler can't check it for you, but you shouldn't do that. Now, lists are the basically go-to data structure in Haskell if you have collection, but if you care about performance, they are not necessarily the best solution. So another solution would be there's this library vector, and you can have vectors of unboxed values. What does it mean for a value to be unboxed? In Haskell, the way it implements polymorphism and also in some sense laziness is that per default, every value is kind of boxed, is a reference to a value. So you just handle pointers, which makes polymorphism kind of easy to deal with because you just copy pointers or do things with that. But if you know anything basically about performance, you know that a memory access is orders of magnitude more expensive than most operations, arithmetic operations. So if you have, for example, an array of pointers to integers and you want to apply an operation to those integers, just referencing all these pointers would be too expensive. So you can say, well, unboxed, that's actually this vector unboxed is a C-style array. And then because I imported this module, now fold and zipWith are the folds and zipWith on vectors, not on lists. Apart from that, the program is the same. It runs a bit fast, it runs faster, but kind of the actual code looks the same. Now, if we want to do the same thing in Accelerate, the code looks almost the same. It's really just one letter in the code that's different. The types are different, but in the code. So, can you spot the one letter which is different in the definition of fold? Oh, for fold, I gave it away. I'm useless. Anyway, okay, fold, it's fold, not foldl. So why is that? Why do you think that might be?
Unordered.
Sorry?
Unordered, like.
Yeah, not quite unordered, but you're on the right track. So a foldl kind of calculates the accumulator from the left. Now we want to have a parallel execution. So what's the kind of standard thing for parallel fold? A tree reduction. So this fold is a tree reduction thing. But what's really different is the type. So it's also vector, but you have these strange ACK things, and also A is not only and doesn't only have to be a number, but also in the eld type class. Now, any guesses what the ACK could be? Thinking about deep embedding? It's an accelerate expression. So basically what this function actually does, it doesn't compute anything on a vector at all. What it does, it takes two abstract syntax trees. So ACK is what expr was in our previous example. So .p here takes two abstract syntax trees and combines them to a new abstract syntax tree. It doesn't compute anything. And the vector is also slightly different, and scalar just means basically one value. So it takes a vector and it returns, it takes two abstract syntax trees which describe computations that result in a vector, and it returns an abstract syntax tree which results in one value A. And the eld type constraint just says, accelerate can't accept all A's you throw in the number type class, because that's not a closed thing. People can throw more in. They are just kind of some types we support as element types. And I'll talk about what they are later, but that's basically where the restriction comes in. And now look at the type of zipWith. So zipWith has something which looks very similar to the expression, just kind of one or less. So this, again, is an expression tree, but it expresses non-parallel computation. So this expresses a parallel computation that results in a vector, and zipWith says, I want a function which takes two sequential basically abstract syntax trees which describe a sequential computation and give me a new one, and then it applies that in parallel. So the type says that the function has to be a sequential function, and the parallelism comes in with zipWith. So I don't have nested parallelism in accelerate. And the type here makes sure that I can't kind of feed, and map has, for example, a simple type map, a similar type map would have an expression A to expression B. So it says, well, map in accelerate can take a sequential computation as argument and then apply that in parallel. But if the computation is already parallel, then it doesn't work. And fold also wants a sequential operation. It also wants, and that's something we can't express in Haskell's type system, it wants a function that is associative. It doesn't it has to be associative. And if not, it's not undefined, because we have a fixed way to traverse there's a tree traversal, but usually that's not what you want. You don't want to feed them a non-commutative, non-associative function. So let me briefly talk. I don't want to spend too much time on Haskell as a programming language. But there's one mechanism with type classes which we will need later on. So let me briefly talk about that. So I said we have this class num, and then we can define instances. So here I said, well, it's already in the prelude, but if you want to declare int to be an instance of num, to be a member of this type class, you say num int, and then you provide the definitions of addition. The definition of addition for floating point values and integer. In the machine level, these are completely different operations, even though conceptually for us they are closely related, but I mean, they would be very different. And the way it's implemented in Haskell type classes is actually that the compiler, it's really just kind of syntactic sugar. A bit more like just purely syntactic, but almost just syntactic sugar. So the compiler gets rid of type classes at all and translate this into just regular system F. Does anyone know what the compiler does? If I have a function like this foo, which has the type given something of type class num, returns something of type class num, what it translates this function to? Exactly. So what it does, it replaces basically the implication thing with a regular function arrow and says, well, give me what's called a dictionary. And the dictionary is just, in case of num, a tuple or a struct with the implementation for addition, the implementation for multiplication, like with all these functions. And then it adds this dictionary as an additional parameter, and then it replaces the function, every function, for example, the function multiplication, it replaces this with a projection into that dictionary. So in object-oriented languages, an object calls a v, usually carries basically a table with it, a v table, where all the methods for this object are stored. And then if you call the method, then the object basically picks the table. So it's a data-centric language, and the data knows what to do. In the Haskell is a functional language, and here the function kind of knows what to do. It's a similar idea, but basically the responsibility is shifted from the data object, which wouldn't work in a functional language, to the function. So really, all this type mechanism stuff is basically injecting such a dictionary, and then the functions are projections. The one problem with that, or problem, yeah, a downside, is that in general, in Haskell, most cases, you cannot type not annotations, and you really should. It's good style. It's good because, well, the type checker can catch more errors. Whoever has to read your code can already guess kind of what you wanted to do by looking at the type, but you don't have to. But with type classes, that may be necessary. One example is like you have the read function in Haskell, and the read function in Haskell has this type. If A is in the type class read, then given a string, read parses the string for you and tries to interpret the string as something of type A and returns it to you. But if I say now read of 5, where should it now, like how should it know what I want it, what the string should be interpreted as, right? It doesn't know, it doesn't have the dictionary for it, because without knowing the type, because it could be a floating point value, it could be an integer. Even if it could already understand the string, it wouldn't be clear. So if I add the type annotation here, then basically providing the type annotation gives it the dictionary. Lets the compiler decide which dictionary it is, and then it calls the parse function for and if I want to list, so then I can tell it it's a list, and then it parses, it converts the string into a list. And this is actually, and you can do the same for a user-defined data type. You just have to say, for example, deriving read, and then it will derive a parser for you, which is really convenient. But anyway, my point was basically that, yes, you gain something from type classes, but the price you have to pay is that you sometimes have to provide information because it can't necessarily automatically figure out what it is. Now, so far, what's the deal usually? Usually it's a bit late maybe already for the break. In general, would you prefer to have a break after 40 minutes?
40 is not that long.
Okay, if you change your mind, that's fine, like just start yawning or kind of falling asleep and I'll get the hint. Okay, so I just showed you how to kind of create this tree, but I didn't show you how to do something useful with it. So you need this function run, and here we have again type classes. It says A has to be array, so that means it can be one array or many, or like, ignore that for a minute. Basically just something that an accelerate computation can return. So run takes an accelerate computation, compiles the thing, runs it, and gives back an A. Now this is clearly like something where the type is a bit is cheating a little bit, because obviously it kind of pretends here to be a completely pure function, which, right, there's no I/O. It doesn't say it's an I/O action, but it compiles a program, it writes it to a file, it runs it. But it's still basically kind of from inside of the function, it's viewed as a pure function, even so that's just true at one abstraction level and not really true. But in some sense, the kind of side effects are always a matter of abstraction, right? Because even evaluating addition has, of course, side effects on the state of your machine. But yeah, so it does. So it takes this tree, generates the program, runs it. And for example, here my accelerate program is .p applied to vector 1 and vector 2, and I can use run to execute it. For example, I can say, well, run this and then show and print the result out on standard I/O. Can anyone see a problem with this? A problem kind of performance-wise?
Every time you run the same program?
Well, yeah, so let's say, so if I run .p just once on one set of input values, that's fine, right? It just does that. And it compiles it once and it runs it once, so that's okay. But you're right, if I run .p on lots of different input values and I use run really compiles all the arguments into the program. So if I apply .p to another set of arguments, it's another program, and it would mean kind of you had to recompile it. Clearly, that's not okay. That's, in general, not what we want. Sometimes it can be useful, though, so because what it does, because the input values basically are compiled into the program, only run a big kernel once, then it can specialize it to that input. So it's not always nonsense. So there's a reason why run as it is exists. But in general, what you want is this run one function. It takes a function from basically ACK A to ACK B, and then it compiles this function and takes an argument A and then feeds already now at compile time exactly what you want to run it with. Then you can compile the accelerate program at Haskell program compile time. And then it doesn't count towards the runtime cost of your program. And run Q does that. So we saw that basically accelerate expressions have these two distinct types. One are the kind of embedded sequential scalar expressions, which we use for map, for zipWith, and so on. And then we have the embedded array computations. So if we look at this, both of them, xbint and xscalarint, are computations which return one single integer value. But the difference is that this is in general a parallel computation which returns one integer value, whereas this is a sequential operation. So this makes sure that kind of, because we can't, on the architectures we're compiling for at the moment, basically, we can't express nested parallel computations. So we want to make them not expressible. And that is almost true. There are kind of some ways, if you use indexing, and like there's a certain combination of things you can actually use where there was a trade-off basically between the convenience. We could have defined it in a way to make it completely impossible, but it would have made it a lot more inconvenient to use. So there's this caveat here that it's only... and if we look into the actual definition of the expression thing, it's... expression A is this algebraic data type, a GADT, just like our arithmetic expression example from the beginning, with lots and lots of different constructors. So one thing I kind of didn't mention explicitly when I talked about GADTs is that GADTs can have in the definition of the constructor a type, a class constraint. And so this means basically, if you kind of remember what type class constraint actually is, it is this additional parameter. So this means that const here doesn't really get just one parameter. It gets a dictionary and a value. So, and then prim up is the application of primitive functions, scalar functions, and so on. Now, we have one problem. We basically want to have in accelerate, we want to overload the usual operators. So we define expression of integers to be an instance of num. So we can use addition to combine two expressions. For example, in the dot product, we used multiplication, right, and we used addition, which looked like the multiplication and addition, like the regular arithmetic multiplication and addition. But in reality, the addition is also basically lifted into this world, and what it does, it constructs this, this tree. And now it has to do kind of one tricky thing, because we have the dictionaries in Haskell land, but it has to kind of plug the dictionaries into the abstract syntax tree. And that's what is done basically with this num type thing. So we use that to annotate. So at code generation time, we now, from regular Haskell, basically, we can look at it and we can see what the operations actually are. So, in the way this trick works, and it has to do with the way class constraints are resolved, is that, let's say you have some data type foo, which has one constructor foo that takes an A and gives you a foo of A. If we don't have GADTs, if you have regular algebraic data types, so it's just A foo of A, then foo and bar should be the same. So what do they do? Foo gets one argument of type foo of A, one argument of type A, and it just returns x plus 1. So it doesn't even look at the first argument. The second one kind of looks at the data constructor, but doesn't look at, you probably, I never mentioned that underscore in Haskell means an anonymous variable. So whenever you don't care about a value, let's say you have first of a pair, you get a pair x of y, and you only return x. Then, because it's really hard to come up with new names for variables, and it's pretty useless to come up with a name for a variable you won't use, you can just use underscore in the function definition. This means there's something there, I don't even care about giving it a name. This is convenient, but it is actually also good practice to do so, because anyone who reads your code, and assuming the function has more than 3 characters in it, immediately knows if there's an underscore that this variable doesn't really influence the value of this definition, so it's quite useful. Anyway, so you would think kind of, and that's true for regular algebraic data types, that foo and bar are exactly equivalent, right? Both really don't do anything with it. With GADTs, though, so and what should actually happen if if foo is a regular ADT without this type constraint, what would happen if I write these two definitions? I get a type error because I have an x and I apply plus to it, but who tells me that x, like it's an A, right? It's not a number, it's not a dictionary constraint. So I get a complaint from the type checker that there's no instance for num of A for this pre-variable A.
If you put a num A annotation in there, it would be fine, right?
If I put a num A, so we can like try is the might.
Because it won't infer without the annotation.
Yeah, so let's do it here. So if I say foo of first data foo, where foo, and I have a function foo of type A.
So does your
Okay, I need, where can I steal it from? So I need this, this extension, even if it's just, so, actually, yeah, I forgot to, so, okay. And then it complains here because here it did the same thing. Okay. So yes, so it says it complains about this. If I add num of A here, then it's happy. But if I just change it num of A, so if I have num of A here, and I just have underscore here, I get the same error. It complains that it doesn't know how to add A. And then, but if I change it to something which without GADTs really doesn't affect the semantics of the program, suddenly, because now it knows which dictionary to use, because it knows that, well, this is the foo that's created with, like the A-with is created with the data constructor foo, which has this num A restriction, so it can plug in the right data, the right dictionary, and then it suddenly works. And we use that trick a lot to kind of insert the dictionaries into our expression trees in the compilation of Accelerate. Here we've got another 6 minutes, and just, are there any questions so far? Then we can do a little bit more. So we also had we had these two expression types, exp and ag, but we also had two argument types. We had vector and scalar. And vector and scalar are really just type synonyms for the more general array data type in Accelerate. So in Accelerate, an array, it's shape polymorphic. It can work with multidimensional arrays. So an array is parameterized by a shape. Only fixes the dimensionality, not the shape type. Only says like how, whether it's a scalar, a vector, a matrix, a three-dimensional matrix, and so on, and the element type A. And shapes have the following form. So a shape can either be Z, which it's basically like the unit type, which it's a type that has only one element in it. And here we have this type synonym, and so, well, a zero-dimensional shape is called Z, and scalar of A is just a type synonym for an array of dimension 0. And then we have this other case, and this is more confusing, like looks more confusing than it is. This is really the colon dot thing is just pair type as an infix thing. So it's that this is an infix type and data constructor, and it says give me two types, A and B, or head and tail, and I'll give you back a pair of this. So it really just bundles them, but we don't call them pairs, we give it a different name. So it's kind of these SNOC lists, so they are kind of nested to the left, right? We have 0 or 0 int, and so on. Right, and that's just the shape. So the type tells me basically the type is more or less a tuple of an n-dimensional matrix is an n tuple, and then the value basically describing the actual shape contains the size. So, and then all the operations, so I said we can't have a map of a map, but all the operations, or almost all the operations in Accelerate are shape polymorphic. So I can apply a map to an array of any dimensionality. So this type really says, give me an array of any dimensionalities with A, and I apply the function to all of them. zipWith says the interesting bit here is only that the dimensionalities have to be the same. So I can give you two vectors, two one-dimensional vectors, and then zipWith works. They don't have to be the same size. It takes the result is the size of the shortest. But they have to have the same dimensionality. I can't zip a vector in the matrix. But I can zip a vector of size 10 and a vector of size 20, and I get a vector of size 10 back. And fold is a bit more interesting. What fold says, it wants at least, as an input vector, at least something of dimensionality 1. So the inner shape can be anything, but it has to have at least dimensionality 1. So it can't be a scalar value. And then the result is 1 less. So if you put in a vector, it gives you a scalar value. If you have a matrix, then it squashes basically the innermost dimension. And that's like if you have an n-dimensional matrix, you get back an n-1 dimensional matrix with fold. And then if you want to basically fold in other directions, so the default is the innermost dimension. If you want to fold in other directions, you have to first reshape it and then fold. And there are kind of slice operations and so on. And then there's one function which is actually really, it's fairly powerful and pretty useful. So the function generate, which gets a shape as an input, gets a function that given an index, something of shape, returns a result. And then it applies that kind of to every, it initializes an array of shape sh by applying this function to every index. So you can kind of create a vector of size 0 to 10 by just applying more or less the identity function, like one thing which takes the index out and returns that to create that. But it's pretty powerful because you can do a lot of things with it. But, so the very last thing to say is that I was kind of lying when I gave you the type of the dot product. but only a little bit. So it's true, it had that type, but it has a more general type. I told you that dot product took two vectors and would give you a scalar. And that's what it does if you give it two vectors, but it has this more general type because both fold and zipWith can work on multidimensional arrays. So it has, in reality, the type that it takes two arrays which have kind of an inner shape, like the dimensionality n+1, and gives you back an array of dimensionality n. Okay, and that's it for today.